Welcome back. In the last video, we discussed that the computer starts off with a random linear model to separate our data, calculates the errors associated with this model, and then readjusts the weights to minimize the error and properly classify the data points. We then stopped at the following question. How does it actually calculate the error? Well, we're going to need a continuous error function. We'll call it E. Looking at this diagram, clearly there are two misclassified points. We know the blue points need to be below the line, and the red one above. So what's going to happen is, this error function is going to assign each misclassified point a big penalty. As for the correctly classified points, they're going to receive very small penalties. We'll have it such that the size of the points reflects the size of the penalty assigned to them. The misclassified points have the largest penalties since they are misclassified, and what we'll do is detect these error variations and thus figure out in which direction we need to move the line the most. The total error then results from the sum of these penalties associated with each point. We'll safely assume that the total error is very high. So what we'll do is actually move the line in the direction with the most errors. We keep doing that until all error penalties are sufficiently small, and thus we're minimizing the errors as we adjust the weights of our linear model to better classify the points, and thereby minimizing and decreasing our total error sum. Now, what is this error function? In order to answer this question, let's rethink our perceptron model. In the second node, based on the score of each point, it predicts a value of 0 or 1. Any point with a positive score gets a 1, otherwise a 0. These are discrete predictions, which are derived from our step function. The problem with this being, a step function increases or decreases very abruptly from one constant value to another. There is no in-between. Based on the value of the linear combination, the step function is discrete. It's not continuous, it's discrete in the sense that it only predicts values of either 0 or 1. Instead of representing our predictions as discrete values of zeros and ones, they need to be continuous probabilities, which is why we cannot use the step function. Because suppose we wanted to predict the likeliness of someone who is, let's say, 62 years old with a blood sugar of 7.5 millimoles per liter. We want to predict the likeliness of this person being diabetic. The value of that person's linear combination based on this model is negative 0.1 times 62 years old minus 7.5 plus 14. All of this equals 0.3. As expected, it's a positive value since our point is below the line in the positive region. Our step function would simply check if that value is bigger or smaller than 0. In this case it is, so it predicts a value of 1. This activation function doesn't actually return the likeliness of someone having diabetes or not. It's either a yes or a no, a very firm value. Well, instead of a step function, to determine the probability of someone being diabetic, our activation function is going to be a sigmoid. There are many types of activation functions, but we'll stick with the sigmoid, which is represented by the following equation. What that's going to do is take the value of our linear combination and sub it into the sigmoid function, which returns a value of 0.57, which means that according to our model, this person who's 62 years old with blood sugar of 7.5 millimoles per liter is 57% likely to be healthy, to not be diabetic. Let's say we test a person who's 20 years old with only 2 millimoles per liter of blood sugar. Their linear combination would result in a value of 10. If we sub this value into our sigmoid, 1 divided by 1 plus e to the negative 10, it results in a value of 99%, which makes perfect sense. The younger someone is, the more they tend to exercise, and generally speaking would carry less weight as opposed to when they're older. And the lower the blood sugar, the more effective insulin is in storing sugar inside the cell, the less diabetic risk. In other words, the further you are from the line in the positive region, the lower your blood sugar, the younger you are, and thus the more likely you are to be healthy. The more you're in the positive region. And obviously the opposite occurs as you go into the negative region. As far as errors go with the sigmoid activation function, let's go back to this data set and assume everyone in blue has already been tested, and we've determined they are not diabetic. They already have a label of 1, and everyone in red has also been tested we've determined they are diabetic. They are already labeled as 0. This is our training data. Our algorithm will try and classify this data, and it will start with some random line. Looking at this data, we can see that this point is misclassified. If we know that the person isn't diabetic, then his predicted probability of being healthy by the neural network should be higher than 50%. However, according to our linear model, this person is in its negative region, which is an error. By adjusting both the weights and bias of our line, it then makes the correct prediction. Going forward, we'll be using the sigmoid function as the activation function, not the step function. That is, we'll proceed with the notion of what is the probability of someone being healthy or not, instead of it being a discrete yes or no. That is all for the sigmoid function, predicting the probabilities of our points. In the next video, we'll go back to our code and implement the sigmoid function onto our existing data points.